This optimization problem wants us to find the area of the rectangle ABCD and the final dimensions which will maximize this area. Infinitely many rectangles can be inscribed in any circle, but this circle has a diameter of 10 centimeters. In other words, the radius of this circle is 5 centimeters. We're told that ON is x centimeters. Because the radius is 5 centimeters, we cannot extend that x value to be any more than 5 centimeters. So there is a boundary on the value of x. It cannot be 5 centimeters and it cannot go beyond 5 centimeters. So x is less than 5, not equal to 5. There's another restriction on x. The fact is that x cannot actually be 0, because if you hit 0, then there is no rectangle possible anymore. And we can just sum it up saying 0 is less than x, which is less than 5. Now, to construct the formula, we need to write it in terms of one convenient variable, for example, x. And as we know that the area of a rectangle is equal to the length times the width of it. Now we know that the length is going to be AB length by CB length. So because we know that AB is twice x, we can write that this is 2 times x. But what is actually CB? So let's have a look at CB. Okay, so CB, I'll rewrite this again, is really 2 lots of CN. And let's just say that CN, we'll call that Y for this particular occasion. So in reality, so I'll just put this as Y. So our formula is 2x plus 2y. Now, as I stated before, I don't want to use 2 variables. I only want one variable, and here I have 2 variables. I've got an x variable and a y variable. So I want to change this y variable so that it all is x. So I'm going to use the Pythagoras theorem, because when I look at that triangle here, CN, and I've called it y, and this is x, and my radius was 5, I should be able to find the value of y, because I can say that x squared plus y squared is equal to 5 squared. You realize that that is the Pythagoras theorem. And as I'm looking for y, I will rearrange this equation so that it is 5 squared minus x squared, and then rearrange further so that this is the root of 25 minus x squared. Okay, so I can now substitute in here, in my for my area, 2x times, that really doesn't look like times, does it? 2, and substitute the value for y, which is 25 minus x squared. The area in this case is equal to 4x root 25 minus x squared. Now, as we're wanting to find the dimensions which maximize this area, we will need to differentiate this formula. To make it more friendly, I'm going to rewrite this again as area is equal to 4x to 25 minus x squared, and use it in its exponential form because it'll be easier to differentiate. Okay, differentiating this is going to need to be we're going to need to use the product rule and the chain rule as well. So we'll start off with saying that u is equal to 4x, differentiate u is 4. Look also at v is equal to 25 minus x squared to the half, and this is where we use the chain rule. So v dash is equal to a half 25 minus x squared to the negative a half, and need to multiply this also now by minus 2x. The 2 and the 2 cancel, so we just get minus x 25 minus x squared to the negative a half. Now when we want to put it together, it'll be u dash v plus u v dash. That's our formula. So let's fill it in. 4 times 25. Again, simplify this. And the reason we were differentiating this is so that we could make this dA over dx equal to 0, so that we can find the value of x when all of this is 0. Now that does not make it really easy for us to find out, so we need to continue simplifying this. I'm going to rewrite this and this in third form. Putting it under the one denominator means that all I'll have to do is multiply this by 25 minus x squared over 25 minus x squared. What actually happens if I multiply these two together? I will get, and now I can put the whole under this 25 minus x squared. And this, just to change color, ends up being 100 minus 4x squared minus 4x squared over the root of 25 minus x squared. Much easier now. I've got for 100 minus 8x squared over root 25 minus x squared. Right, so that's my dA over dx. dx. So what's the value of x when dA dx is equal to 0? What makes this equation 0? This equation is only 0 when this numerator is 0. What actually does the denominator tell us is a different thing altogether. It tells us that x cannot be equal to 5. Which is what we put our restrictions already on this. So let's just work through the top bit and say, okay, so 100 minus 8x squared is 0. X squared is equal to 100 over 8. Now I want to demonstrate to you that as long as you do right maths, you can do this two ways. So I'm going to, on this part here, I'll rewrite this again. Okay, now my left hand side, I could decide that I want to divide both parts by 4. Okay, so that will give me 25 over 2. Whereas on the other side, I might say, no, I'm going to find the root of 100, and I'm going to find the root of 8. Okay, so on the left-hand side now, I now put the root of 25 over root 2. And I can continue and say, well, root 25 is 5 over root 2. But on the right hand side, I've ended up having 10 over root 8. And you think, well, which is the right answer? Well, actually, I can continue with this because root 8 can be once more seen to be as root 2 times 4, which indicates that that could be root 10 over root 2 root 4, which means that it's 10 over 2 root 2, which if I cancel that down, I do get down to 5 root 2. Okay, we still get the same answer, whichever way you want. Now, you may have started doing the yellow way, or you may have gone through the red way. It doesn't matter. Therefore, when dA over dx is equal to 0, x is equal to 5 over root 2. Now the value mathematically may be minus 5 over root 2 and plus 5 over root 2, but because we're dealing with lengths here, it's impossible to have a negative length, so x is a positive value of 5. Is this the maximum value or the minimum value? Well, we're going to do a sign test. We know that our x value is 5 on root 2, but we also know that it cannot go below 0 and it cannot go above 5 or equal to. And as this is a sign test for f dash x or dA dx, and we have a look at our dA dx formula over here, let's pick a number, for instance 0, and now replace the x with the 0 in both sides. If we replace it with 0, we will find that we get a positive value here. And if we replace it with something possibly like 5 on this side, we know that we will get, less than 5, sorry, it should be just a little bit less than 5. Then we will know that we get a value of a negative value. That indicates to us that that must be a maximum value. Okay. And the area is maximized when x is equal to 5 on root 2. Our question asked us, what is the dimensions of A, B, C, D? The length of this rectangle is 2x. And our x value is 5 over root 2. That gives us a value of 10 over root 2. Okay, you might also be given, look at this in a different way. You might say that the length is 2 times 5 over root 2. I could rearrange the 2 and change it for root 2 multiplied by 5 over root 2, which gives me the ability to cancel this out, and that leaves me with 5 root 2. Okay, so you can see that I've got this in a different form. The answer is either 10 over root 2 or 5 over root 2. They're exactly the same. And the width of this rectangle is 2y, and that means it's 2 root 25 minus x squared, because that was what y was. And if we substitute x minus, which is 2 root of 25 minus 25 over 2, giving us a width of 5 root 2, which basically says that the length and the width are the same, and this rectangle is really a square of 5 root 2 by 5 root 2. So in this example, I demonstrated that there are sometimes answers which look different but are algebraically the same.